Recording in progress.
So good afternoon. My name is Dr. Richardson. This is lecture 8 of the course entitled An Introduction to Linear Algebra Using Python. My email address is srichards22@comcast.net. Again, I remind you that learning is not a passive activity, so it's important to take notes and not just watch me in the lecture. You are highly encouraged to do the problem sets. They involve an analytical component and a component where a lab component where you will apply Python to problems in linear algebra. Simply taking notes and not doing the problem sets is not advised. You're not going to get much out of this course if you take that approach. Again, you can send me email questions, or you can send me questions by email anytime, and I promise to get back to you within 24 hours. And you may find a ruler helpful. Let me say one thing about lecture 7. If you noticed at the break, we didn't continue the lecture. We ran into technical difficulties. So what we're going to do in lecture 8 is pick up from that point, the break point from lecture 7. And this afternoon, we'll talk about matrix multiplication revisited beyond 3 dimensions, looking at vectors in Rn, n-dimensional spaces or n-dimensional vectors, complex numbers, and the inner product of vectors. So I want to pick up from where we were last time, and I want to review, in fact, some things that we talked about last time. So you can take everything we've talked about in lectures 1 through 7 and boil it down to this problem, where you have on the left-hand side of this equation a matrix. On the right-hand side, on the left-hand side, you have that matrix multiplying a vector. So this is an example of matrix vector multiplication on the left-hand side, and the right-hand side, you get a vector. So all systems, if you want to solve a set of systems of linear equations, you can boil them down to a simple expression. That expression is simply this matrix vector multiplication. Again, we saw last time that x and b are vectors, but all vectors are also matrices. It's not true that all matrices are vectors. So what does my matrix vector equation mean? How is it that this simple little concise equation contains a wealth of information? How do we get that wealth of information? So we looked at some case studies last time, and I'll review these. So the first case study is where you have A, and it is a non-square, or actually, I wanted for case 1 to be consistent with what we did last time. I want it to be a square matrix. So it's an n by n square matrix. That's the first case we looked at. So this means that our matrix A has n rows and n columns. My matrix of unknown, or my vector of unknowns x, has to have n rows and 1 column. If I might multiply those two creatures together, matrix vector multiplication gives me another vector that has n rows and 1 column. So if in fact the matrix A is non-singular, that means that its determinant is not 0. And it also means that the inverse of this matrix A exists. And we've discussed that in previous lectures. So that means you can take the inverse of A and left multiply this equation. And since the inverse of A times A is just the identity matrix, that left-hand side simplifies. And in fact, you will discover in this particular case that you have a unique solution to the problem. So unique solution exists. To find that unique solution, all you have to do is calculate the inverse of A, multiply it by B, and that'll give you A. And you'll have some practice examples with this on the problem sets. So the next case we looked at case 2. Regarding the problem sets. So the solution key to problem set 7 is available, will be available this evening, and problem set 8 will be posted probably sometime late tomorrow. Okay, so the next case involves a little wrinkle of case 1. Suppose I matrix A is still a square matrix of order n. It has n rows and n columns. But in this case, let's assume that the matrix is a singular. That means that its determinant is 0. So you cannot write down an inverse for A. So this inverse does not exist. So that tells you you're not going to get a unique solution like you did in case 1. So this equation for this case does not possess a unique solution. So that has to imply one of two things is going on. There's either no solution to the problem or an infinite number of solutions. One of those things is in play. Okay, and that's consistent with case 1. Okay, so how about case 3? So suppose you have the special case where your constant matrix or constant vector is the 0 vector. And here in case 3, we'll assume that A is a n by n square matrix. Well, clearly, x equals 0 is, and again, I should be careful, this is the 0 vector. This is a solution to this problem for case 2, but it's a trivial solution. Just as if you take the matrix A and multiply it by a 0 vector, you should get the 0 vector. Now, suppose there exists a non-trivial or non-zero solution to this problem, which we'll call x, for which my matrix multiplication is true. So we write this expression down, but we have to think about what it means. So we'll underline it. Well, this is true that a non-trivial or non-zero solution x exists, then A cannot have an inverse. Why? Because if A had an inverse, then you would be able to write this equation down, and there's clearly a problem here. There is no matrix that can bring the 0 matrix back to a non-zero vector. There's no matrix you can come up with that'll do that. So, in other words, if in fact you have a case where A times x equals 0, where if A is a square matrix, then there only exists a non-trivial solution. You always have the trivial solution, but a non-trivial solution will always exist if and only if the determinant of A is 0 or A is singular. And this is an extremely useful, I'll call it a theorem, that you use many, many times in science and engineering. Problem is sometimes in terms of applications, you just state it and run with it. But it's also important to see why it's true. Okay, so we've looked at 3 cases so far. Let's look at case 4. So here's a case where you have a matrix equation, but now I'm going to let A be a rectangular matrix. She's either wide or tall. So it has m rows and n columns. To satisfy the rules of matrix multiplication, x, my vector that contains all the unknowns in the problem, has to be a vector that has n rows in one column, and the 0 matrix has m rows and 1 column. Here, A is a n by n matrix. It's rectangular, it's either tall or wide, depending upon the relationship between m and n. And solutions to systems of linear equations that meet this form, we've looked at in some detail before. And we've discovered that if you can calculate the rank of the coefficient matrix and compare it to the rank of the augmented matrix, and if that is in fact equal to the number of unknowns in the problem, then in fact a unique solution exists. So just writing this down doesn't really tell you whether you have a unique solution, an infinite number of solutions, or no solution. One suggested guide to answer that question is to actually go through this application of using the rank of a matrix that we define by using determinants to actually see how these two creatures are related. You can similarly find out, once you calculate the rank, that in fact the rank of these matrices, that if in fact the rank of the coefficient matrix A equals the rank of the augmented matrix, but both of those guys are less than the number of unknowns in the problem, then you have a case where there are infinite number of solutions. So case 4 is far more general or complicated than the previous two cases. And finally, the third and fourth criteria is if you found that the rank of the coefficient matrix was in fact less than the rank of the augmented matrix, then no solution would exist. Now you should think about it for a minute, that this augmented matrix and this coefficient matrix are interesting when the case where b equals 0. And I'll just leave it at that. Think about this in relationship to the previous criteria. Okay, finally, and this is where we stopped last time. So there is a final case, case 5. And here I have my most general form using matrix vector multiplication for a system of linear equations that I want to solve simultaneously. But as in case 4, I want this matrix A to be rectangular or wide or tall, not square. So A has m rows and n columns. X has n rows and 1 column. B has m as in micro rows and 1 column. And again, whether or not you have a unique solution for the problem, whether you have an infinite number of solutions to the problem, or whether you have no solution to the problem, really depends upon the relationship between the rank of the coefficient matrix and the rank of the augmented matrix. So in fact, if those two creatures are equivalent, where little n is the number of unknowns, then, as we saw in case 5, a unique solution to the problem exists. And all of these cases, 1, 2, 3, 4, 5, we have gone through concrete examples of them through the problem sets by just looking at specific cases using numbers. But if you step back and look at this problem 37,000 feet, you can write this problem in a completely general form like this and analyze what's going on. And again, as we saw before in case 4, if in fact the rank of A equals the rank of the augmented matrix in a problem, but that's less than n, the number of unknowns in the problem, then you have an infinite number of solutions. And finally, if the rank of the coefficient matrix is less than the rank of the augmented matrix, then no solution exists. So at the end of the day, it's very nice and beautiful that you can use matrix multiplication, in particular matrix vector multiplication, to write all the possible cases that you can encounter when you solve a set of linear equations simultaneously as this simple equation, which, as I said last time, is one of the most important equations in linear algebra. Some would say it is the most important equation in linear algebra. Okay. So next, armed with this ability to recognize vectors as being matrices, we can go back to a number of problems we've talked about and get, or a number of ideas that we've discussed, and get better insight into what's going on. So let us return to solve some previous questions. Okay, so question number 1 that we're going to return to is, why do we use our rule for matrix multiplication? In other words, we wrote down a rule that allowed us to multiply matrices together, but we really never gave any justification for why we picked that rule and not another rule. So let's look at a nice example. We'll pick 2 linear equations that are simple to clearly see what's going on in terms of the ideas. So here are 2 equations and 2 unknowns. You can pull from these 2 equations a coefficient matrix. You can also recognize from this problem that you can define a matrix, a constant matrix, which in this case is a 2-by-1 matrix. My coefficient matrix is a 2-by-2 matrix. And I said that if I want to multiply these matrices, and there's a third matrix in this problem, the matrix of unknowns, X, and that's just a matrix that has 2 rows and 1 column. So there are 3 matrices I have to worry about. And the problem I want to focus on, why do I go through the trouble of defining matrix multiplication, where I have a 2-by-2 matrix multiplied by a 2-by-1 matrix, and I take the first row of the first matrix and multiply it by the first column of the second matrix. I'll get 3 times x of 1 plus 2 times x of 2. And then the 2, 1 matrix element comes from taking the second row of the first matrix and multiplying by the first column of the second matrix. So I get x of 1 minus 4 times x of 2. It's a little sloppy, so let's clean that up a bit. That's a little better. So my result is a 2-by-1 matrix, and that equals B, which is a 2-by-1 matrix. Now you can see something very interesting. If you in fact equate these two guys, you get back the original system of linear equations. So this definition of matrix multiplication leads to a natural way of expressing our original set of linear equations. And that's the justification for it. So matrix multiplication, at least the way we've defined it, and most people have defined it, so our definition, it's not all that mysterious once you understand that vectors are matrices and you learn about matrix vector multiplication. Matrix multiplication, our definition, is a natural way to express our equations. So in other words, this matrix vector equation leads to our set of linear equations, two equations and two unknowns, if we define matrix multiplication in our standard way. So just writing this matrix multiplication down is useful. We've done that in previous examples, but we see now why we did it that way. We do it that way because it, in fact, is a very convenient way to go back and forth between the general matrix equation and specific systems of linear equations. Okay. Second point we want to revisit. Now that we have a better feel for why we multiplied matrices the way we did in the past, there is another way that we can view matrix multiplication. And I want to see that by going to an example. So suppose I define three matrices, or three vectors, U, there are 3 rows and 1 column, V, and W. So I'm just picking in my example 3 vectors. So let us take a linear combination of these 3 vectors. We'll do that in equation 2.2. We know what we mean by a linear equation, or sorry, a linear combination. We certainly know what we mean by a linear equation, but I was referring here to a linear combination of vectors. If I take a scalar C and multiply it by a vector U, and add that to what I would get if I took a different scalar D and multiplied her by a different vector, in this case V, and then add that result to what I would get if I get another scalar, take another scalar E and multiply it by a vector W, which is that in this case. And if we spell this thing out, the way we can spell this out is we multiply the scalar by the vector, so that's scalar multiplication. And then we add those vectors together. We will discover the following. C times this vector plus D times this vector plus E times this vector will all sum up to give you a new 3×1 vector. These vectors are 3×1, so when you add them, you should get a result that is also a vector 3×1. And it has three components: C, D minus C, and E minus D. And let's call this guy star. So the thing that's new here is the answer to the following question. Can we rewrite, so we have a linear equation, a linear combination of, we keep talking about linear equations. Here I have a linear combination of three vectors. I get a result C, I get a result star. Can we rewrite this linear combination? That's the question that's being posed on the table at the moment. Can I rewrite this linear combination as a matrix equation? And the answer is yes. So how would I do that? Well, I want to take the left-hand side of 2.3 and write it as a matrix equation. So I can state this, but if you sit down and look at this, you'll see it's got to be true. If I take the first vector and write it as a column of a matrix, the second vector and write that as the second column of a matrix, the third vector and write that as the third column of a matrix, that's a 3×3 matrix. I then multiply that by a 3×1 matrix that contains the scalars C, D, and E. And if I use the ordinary rules of matrix multiplication, it's easy to show that that gives you a 3×1 matrix, which again is star. So what have I gotten here from all this work? I have shown that the left-hand side of equation 2.3 has to be equal to the left-hand side of equation 2.4, since in fact the right-hand sides are equivalent. Let us before we make that jump, let us recognize that equation 2.4 is really an equation has a matrix where this first column, C sub 1 is the vector, first vector, C sub 2 is the second vector, and C sub 3 is the third vector. In this example, they were U, V, and W respectively. I get a new matrix on the right-hand side, what I've called star, D, D minus C, C, D minus C, and E minus D are its matrix elements. And now if I equate equations 2.3 and 2.4, and again, it's not a problem. I mean, you can at your own peril, skip some of these steps, but it's useful just to flesh this whole thing out. See how everything is working in this particular example and generalize later. I've discovered something interesting. Matrix multiplication or matrix vector multiplication, where I multiply the matrix A times the vector X, is exactly the same thing as taking the linear combination of the three vectors U, V, and W, where U is the first column of A, V is the vector, excuse me, which is in second column of A, and W is the vector, excuse me, that is in the third column of A. So you have at your disposal another way to express what happens when you multiply a matrix A by a vector X. That way is the matrix A multiplied by the vector X is the same thing, excuse me, as a linear combination of three vectors U, V, and W, where U, V, and W are the columns of A. Excuse me. So I could write A in that form. And X is simply a matrix of scalars. It's the scalars that you used in the linear combination. So that's shorthand notation for this. So let's summarize. Someone gives you a matrix A, asks you to multiply it by a vector X. You can get a result B, vector B, and you can write down what that is, what B is, using the conventional way of matrix multiplication that we've been using throughout this course. So that's one way to look at this matrix vector multiplication. Another way is to recognize that B is simply the linear combination. And let's write this in its most general form. Excuse me. B would be X sub 1 times V sub 1 plus X sub 2 times V sub 2 plus all the way up to X sub n times V sub n, where my scalars X sub 1 and X sub 2 are just components of an n by 1 matrix of unknowns, and V sub 1, V sub 2, V sub 3, all the way up to V sub n are the columns or column vectors. These are the columns of A. Okay, So let's pull all this together and let's go through a nice example. So suppose someone gives you a 3x3 matrix. And you are given a 3x1 matrix of unknowns. And you want to do this matrix multiplication. So this new way of looking at life is to recognize that my original matrix has 3 columns. It's a 3x3 matrix. Those columns those columns each have column vectors. So in fact, this can be written as a linear combination of those column vectors. And the scalars in the linear combination are just given by x, y, and z respectively. So I have 3 terms here. I have x times c sub 1, which is the 3x1 matrix that looks like that, plus y times c2. She is 3, 1, 0. And let's see, I'll continue this over here. I don't have to fall off the screen. C sub 3 is just the 3x1 matrix 1, 1, 3. Okay, you can use the rules of scalar multiplication and vector addition. And you'll discover you'll get 2x, 8x minus x plus 3y, y 0 plus z, z, 3z. We'll add those 3 vectors together and you get a 3x3 matrix, 2x plus 3y plus z, 8x plus y plus z, and minus x plus 0 plus 3z. So the amusing thing about all this is that if you go back to the original problem, and just use the conventional means of matrix multiplication, you will discover, I'm not going to do it, I'm going to let you do this, is that you will get exactly the same result. So that shows that these 2 schemes of matrix multiplication are equivalent. So let's summarize. I claim that I can write down any system of linear equations that I want to solve simultaneously in this nice, simple, concise form. One of the beautiful things about linear algebra, it allows you to take complicated expressions and write them in terms of very succinct, simple matrix equations. And this is one example of that. Now, I know something more about B. B is a linear combination. So here we've defined the idea of a linear combination before, but now we see here why it's useful. It's a linear combination of the columns of A, where X contains all the scalars in this linear combination. So if we want to write this out in all full glory, then what this matrix equation is telling us is this has to equal x sub 1 times c sub 1 plus x sub 2 times c sub 2 plus dot, 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 x sub n times c sub n, where the scalars all belong to the matrix of unknowns. This matrix of unknowns is n by 1. And C1, C2, C3, these are vectors, and in particular, they are the columns of the matrix A. So we are going to use this expression later on in the course when we talk about the least squares approximation. But I thought it would be much more useful and helpful to see where it comes from now. We're at a stage to see exactly where it comes from, rather than waiting to explain where it arises later on. Okay. So let us put all this stuff together and go through other examples. And again, we are revisioning. We're looking at matrix multiplication in a new light. And let's pick an example that's simple. So here's a 2 by 2 matrix, a square matrix of order 2. And we're going to multiply it by a matrix of unknowns. In order for matrix multiplication to be compatible, this has to be a 2 by 1 matrix. I now know how to look at this operation of vector or matrix vector multiplication. So this is a matrix and this is a vector. And I now how to look at this. I now know how to look at this in a new light. This thing really is a linear combination of the two column vectors of the matrix, and the coefficients that you need in the linear combination are just scalars that come from the vector. So this is a linear combination of column vectors. This is simply 2x plus y and 3x minus y. This result is a 2 by 1 matrix. It has to be. My original matrix is 2 by 2. My matrix or my vector of unknowns is 2 by 1. So this final result has to be a 2 by 1 matrix. It has 2 rows and 1 column. The important idea that we've been talking about is that this result that you got by using the idea of linear combinations of column vectors is exactly what you would have gotten using the conventional method, where you wrote down the problem and looked at the first row of column of matrix 1 and multiplied it by the first column of matrix 2. So you would have gotten this here. But before we go any further, let's look at this with a better, more powerful microscope. This result is what you get if you take the dot product of row 1. If you look at row 1 as a vector and you take its dot product with column 1 viewed as a vector, then that's exactly what you get here. And the second result from our conventional scheme of matrix multiplication says you take the second row of the first matrix and you multiply it by the first column of the second matrix. So that's equivalent to taking the dot product of row 2, which is just a row vector, with column 1. And in that case, it's just 3x minus 1. And that's what you get here. Okay. So two things. In matrix multiplication, matrix vector multiplication, you have two approaches. One approach is the right result. It's a linear combination of the column vectors of the original matrix. Another approach is to use our conventional scheme of matrix multiplication. But if you look under the hood of that truck, that scheme really says to take the dot product of the row vector of the first matrix with the column vector of the second matrix. That gives you the first matrix element here. And then take the dot product of row 2, or the vector in row 2, with the column 1 in the second matrix. Or I look at column 1 as a vector. And I know how to take dot products. And this result should give me that. So again, both schemes give you the same answer. You get the same 2-by-1 matrix, but you also have a better appreciation for why linear combinations are useful, and you have a better appreciation for what you really are doing in the classical definition of matrix multiplication. You're taking dot products of vectors. You just have to be careful which vectors are you taking dot products of. And the rules are here. Okay, so to really see that we know what's going on here, let's extend this example. And let's look at, we don't have to put numbers in here, but let's look at the general case where here I'm multiplying two matrices together. And I will do this in general form, so I'll just write the matrix elements as variables, as constants, A, B, C, D, E, F, G, H. So the problem here is that I don't have, in the previous example, I had a matrix multiplying a vector. In this example, I have a matrix multiplying a matrix. So how do I apply this linear combination idea? And the answer is one step at a time. Namely, if I were to just consider column 1 of the second matrix and look at matrix multiplication with it, with the first matrix, using the idea of linear combinations, I would get E times AC plus G times BD. And that's going to give me, using scalar multiplication and vector addition, AE plus GB, EC plus GD. And you can almost see this is a 2-by-1 matrix. So what you get really is just the answer for the first column of the new result. But you know this can't be complete, right? Because if you multiply a 2-by-2 matrix times a 2-by-2 matrix, you better get a 2-by-2 matrix. So I'm missing some guys over here and here. So where do I get those guys from? Well, if I go back to the original problem, the second matrix has a second column. So what I have to do is take a linear combination of it using the same rules that we talked about before, F times AC plus H times BD. And if I do that, this will give me AF plus BH time and a CF plus DH. So all I'm doing here is multiplying a scalar times this vector, a scalar times this vector. I get two 2x1 matrices. Vectors are matrices. I add them together and I get a new 2x1 matrix. But that is exactly what I need to do or use if I want to find out what goes on in the second column. In the second column, I therefore get what I have here. AF plus BH, CF plus DH. Okay, so let's call this star or triple star. This is a 2x2 matrix. It has 4 matrix elements. There's 1, 1, 1, 2, 1, 1, 2, 2, 2. Now, contrast that with our classical way, not looking at matrix multiplication as taking linear combinations, but our classical way to do matrix multiplication. And all you have to do here, as in the previous case, is recognize that our classical way of doing matrix multiplication really involves taking the dot product of 2 vectors. In this case, the dot product of row 1 of the first matrix with the column 1 of the second matrix. And then just proceeding as always, you'll get a 2x2 matrix. And here are the matrix elements. Row 1 is dotted into column 1. That's the 1, 1 matrix element. The 2, 1 matrix element is row 2 dotted into column 1. The 1, 2 matrix element is row 1 dotted into column 2. And the 2, 2 matrix element is row 2 dotted into column 2. And if you go through the trouble of writing out those answers, those matrix elements, do that, you should discover that's exactly the same as, so this is equivalent to star, star, star. Okay, so this exercise was meant to give you practice in looking at another way to view matrix multiplication in terms of linear combination of vectors. And in the problem set 7 and problem set 8, you'll have ample opportunities to practice this idea. Okay. So the next thing we need to take into account is the fact that vectors are important things in 1 dimension, 2 dimensions, and 3 dimensions. But vectors are not limited to those sets. Namely, if you're looking at points or vectors, points are vectors in R1, that's 1 dimension, you'll get a line. If you're looking at vectors or points in 2 dimensions, that will give you a plane. If you're looking at vectors as points, the art that tells the audience that you're dealing with real scalars. These are real numbers. So if you're dealing with points in 3 dimensions, that's R3. And this is the set of points or vectors in 3-dimensional space. So you might think that a one-dimensional space, a 2-dimensional space, and a 3-dimensional space are all you have to worry about. And that's not the case at all. For example, suppose you have a room with a flying bee running around, and you want to find out where that bee is. Well, you can define the position of that bee with respect to some origin in the room, maybe one of the corners of the room, by a position vector, R. A position vector is like any vector, it has components. So you have an X component, you have a Y component, you have a Z component, but you have a problem here. This B is not stationary. This B moves. So its position will also depend upon time. Lowercase t. So my position vector, R, is a vector, and it has 4 coordinates: X, Y, Z, and T. In other words, if I write this vector in column representation, it's a vector that has 4 rows and 1 column. And it belongs to the set of points in 4 dimensions. Now, there's a problem here. My mind, and your mind also, cannot visualize 4 dimensions. I can easily visualize 1 dimension, 2 dimensions, and 3 dimensions. Our minds were just not built to visualize what 4 dimensions looks like. But that's what shouldn't stop us. That's a physical limitation that we have. And vectors are not slowed down by that speed bump. Okay? In this simple example here, there's nothing wrong at all with defining the position vector of this moving bee in the room, having 4 coordinates. And you know exactly what those coordinates mean. Okay? And in fact, that is the simplest way to describe the motion of the bee in the room. So let me give you another example. Of vectors that are not constrained to be just in 1 dimension, 2 dimension, or 3 dimensions. Suppose I have a class and I have 6 students. So I have students 1, 2, 3. For privacy rules, I won't specify their names. 4, I'll just give them numbers. And my last student is student 6. And suppose I give an exam, I grade it, I give the grades back, and the students discover this is how they performed. Student 1 got 81 out of 100. So this grade is based on 100. Student 2 got 73 points. Student 3 got 94 points. Student 4 got 41 points. Student 5 got 59 points. And student 6 got 61 points. Well, here I can define a vector V, which is just a list of numbers. And in column representation, I perhaps should stop saying that. I'm always going to write my vectors in column representation in linear algebra. That's the standard way I'm going to start expressing them. I can write this as a list of numbers or as a 6x1 matrix. So once I allow the idea of the possibility of lists of numbers, then I'm not restricted to 1 dimension or 2 dimensions or 3 dimensions. I could have had 55 students in the course. Then I'd have a vector that's 55 by 1, 55 rows and 1 column. I could have had a class of 1,000 students. Then I could describe this class by a vector that has 1,000 rows and 1 column, or 1,000 by 1 1,000 by 1 matrix. So a list of numbers, this vector V is a list of numbers, but they're not just arbitrary numbers. They are important numbers because they tell you something about this particular application. In particular, this vector describes the grade of n students in a class. So again, the idea of a vector in 4 or 5 or 6 dimensions is not something that's really all that bizarre once you start thinking about it and recognizing that if you view lists as vectors, which is what the computer scientists do, then you can recognize that linear algebra has a life beyond 3 dimensions, and hence it's extremely useful. So let's take a break now. It's 3:06, so let us resume at 3:15. Okay, so let's continue. So we realize now that you can have vectors in 1, 2, 3, 4, 5, 6, 7 dimensions. And in fact, there's nothing wrong with writing down a vector, which really is a list of numbers, in n dimensions. Or for that previous example we looked at, suppose I had a class and I didn't know, well, okay, I knew, but I wanted to write down a general vector, regardless of whether there were 30 students in the class or 300 students in the class. Well, I can take care of that contingency by just writing a vector with n components. And again, in column representation, vectors are matrices. This is just a vector or a matrix with n, as in Nancy, rows and 1 column. And again, I keep mentioning this, and at some point in time, I'll stop saying it. We are choosing to write our vectors in column representation to start with. So the next logical question you could ask is, what are the basis vectors for V? So this is a vector in n dimensions, where that R tells the audience that all those components are real scalars. So any vector has to have a set of basis vectors that generate or span it. Now you see there's a problem with our previous notation. So there is a problem. With just using I hat, J hat, and K hat. Because as n gets bigger and bigger, I'm going to exceed the letters in the alphabet. So this is why I used that notation before: E hat sub 1, E hat sub 2, E hat sub 3, E hat sub 4, for basis vectors, because this gives me the freedom of going beyond the letters in the alphabet. And these are the basis vectors which span or generate my vector v. So I could write down any vector v. But remember now, a vector is a creature that has magnitude and direction. The direction is given by the basis vector, and the magnitude is just the component. So e hat 1 times v sub 1, e hat 2 times v sub 2, and this goes on to e hat sub n times v sub n. And, you know, why make things complicated? Sigma notation allows you to write down this in a much more succinct form. Okay, now that I have my vector in n dimensions, I can recognize that if I write it in terms of basis vectors, my standard basis, where I have n components, and this is really v sub 1 times a standard basis vector 1, 0, 0, all the way to 0. So I have n components. It's an n by 1 vector plus v sub 2 times this standard vector 0, 1, 0, 0, 0, 0. And I just keep going all the way to v sub n, where I have my final. So this is e hat 1, this is e hat 2, and this is e hat n. The beautiful thing about this is I don't know how to write down. My brain is not designed, was not designed to visualize the standard basis vectors for an n-dimensional space. But I can still express them in terms of vectors or lists of numbers. Okay, so let's see how the existence of vectors in n dimensions jives with some of the other things we've learned about vectors in 1, 2, or 3 dimensions. Suppose I have two vectors u and v. They both have n rows and n columns. And suppose I want to take the dot product of these two vectors. Well, that's just the transpose of u times v. And that's simply using the rules of matrix multiplication. If I take the transpose of u, it turns from an n by 1 matrix to a 1 by n matrix. So I get u1 times v1 times u2 times v2, all the way up to u sub n times v sub n. So what I just said was so useful that it's important to write it down. In this particular example, where u and v are general vectors in n dimensions, I'm taking a 1 by n matrix and multiplying it by an n by 1 matrix. So I better get a 1 by 1 matrix, which is just a scalar. And I do. And note that the dot product of these two vectors is positive unless both vectors are 0 vectors. So it is perfectly logical to look at vectors as creatures that exist in higher dimensions, 4, 13, 79. Going beyond n equals 3. Although our brains cannot visualize them. Now, if that doesn't give you comfort, there's a fallback position. The fallback position is always to look at vectors as lists of numbers. And if you're writing down lists, you're not confined to 3 elements in the list, 3 components in the vector. In this case, I have a 5 by 1 matrix. This vector, which we'll call C. This vector is in 5 dimensions. It exists in 5 dimensions. Okay. A last thing to do with both V and C, for that matter, even though I cannot draw these vectors on a piece of paper, they still have a magnitude or norm or length. I just use the standard definitions. Namely, I take the dot product of those 2 vectors with themselves, and I take the square roots. So for example, in the case of C, I take 121 times 121 plus 8 times 8 plus 9 times 9 plus 12 times 12 plus 13 times 13, add all those numbers up, get a number, take the square root, and that's going to be a number that's 0 or greater than 0. Clearly in this case, it's greater than 0. So the norm of a vector V for any vector in n dimensions is just the dot product of that vector with itself, which gives you a scalar, and then you take the square root of that, and that's just V sub 1 squared plus V sub 2 squared plus V sub 3 squared plus V sub 4 squared, all the way up to V sub n squared. And then you take that quantity in square brackets, take its square root, and that result is a number which is 0 if all of these components are 0, or is a positive number. So let's summarize. For a vector V, I can certainly have a vector V that has a norm in 2 dimensions, and I certainly can have a vector that has a norm in n dimensions. I can certainly take the dot product of 2 vectors, regardless of whether or not they are in 2 dimensions or 3 dimensions. I could multiply or take the dot product of 2 vectors. In one case, they could both be in 2 dimensions. In the other case, they could both be in n dimensions. And there's no limitation. There's nothing wrong with those operations at all. Okay. So I'd like to conclude by at least this part of the lecture to make you more comfortable with vectors in n dimensions. Just view vectors as lists of numbers. And if you use that approach, then there's no reason why you should be limited just to 3 dimensions. Okay, So up to now in this course, we've been talking about real numbers, real scalars. Turns out that there is more going on in the universe than real numbers. We have complex numbers. So complex numbers play a role throughout science and engineering, and they actually do play a role in linear algebra. So what I'd like to do is take a few minutes just to review some central ideas about complex numbers in linear algebra. This is not by any stretch of the imagination an exhaustive discussion of complex numbers or complex variables or complex functions, but it's just meant to get us all up to speed so that we can jump back into linear algebra and be comfortable with this concept, or the concepts of complex numbers when we see them. So where does this all come from? Well, you could have discovered complex numbers or the problem that complex numbers solve in elementary school, or junior high school or first year high school in an algebra course. If you in fact were given this equation, x squared plus 1 equals 0, and asked to find the values of x that satisfy that equation, you'd use the rules of algebra, and you discover that you're in trouble because you have to take the square root of a negative number, and you don't know how to do that. There's nothing that you've seen in your experience of real numbers that would equip you to trying to solve that. So a way out is to invent a new number, which we'll call I. I should warn you that electrical engineers and Python developers do not use the symbol I, they use the symbol J. Electrical engineers do it because in electrical engineering, there's another concept called the current, and it has the same symbol. So electrical engineers don't want to confuse the idea of current with complex numbers, so they use J. And Python developers follow the habit or set of conventions that electrical engineers do. We won't in this lecture. But if you look at the problem, if you look at problem set 8 in the exercises involving Python, it's J that solves this problem here, not I. Okay, so most people use the letter Z to express a complex number. And a complex number has two parts to it. It has a real part, which is denoted by X, and it has an imaginary part, which is denoted by Y. And please don't be confused here. X and Y are real numbers. The thing that makes this thing a complex number is you take the real number X, you take the real number Y, you multiply the real number Y times X times I, and then you add that result to X, and that gives you a complex number. So let's look at some examples of complex numbers. 3 plus I, 9. The real part is 3, the imaginary part is 9. 0 plus I, 13. The real part is 0, the imaginary part is 13. 13 plus I, 0. Now you may say, well, this is just a real number. It's true, but another way to view a real number is that it is a complex number whose imaginary part is 0. What can you do with complex numbers? Do they have an arithmetic? And the answer is yes. So for example, suppose you have a complex number z sub 1. Well, let's define it accordingly. And let's suppose you have another complex number, z sub 2. So that we don't confuse it with z sub 1, we'll define it accordingly. Well, x sub 1 and x sub 2 are the real parts of z sub 1 and z sub 2, respectively. And y sub 1 and y sub 2 are the imaginary parts of z sub 1 and z sub 2, respectively. Suppose I want to add z sub 1 to z sub 2. Well, all I have to do is add their real parts and then add their, imaginary parts and simplify. So I'll get a new result that has a real part and a new result that has an imaginary part. There's nothing wrong with subtracting complex numbers. I get a real part and I get an imaginary part. What about multiplying complex numbers? Well, if I just write down what they are, and I recognize that x sub 1, y sub 1, x sub 2, and y sub 2 are scalars, so I know how to do multiplication with scalars using the distributive properties of scalars or numbers, and I know what to do with I. I know what I means. So I can expand this out and I'll get 4 terms. X sub 1 times x sub 2 plus I times y sub 1 times x sub 2 plus I times x sub 1 times, y sub 2. And then when I multiply these guys together, I remember the definition of I. I is a number, which we've invented such that when you take it square, you get -1. So this last term has to be minus y sub 1 times y sub 2. So this is x sub 1, x sub 2. And I want to group all these things together. This becomes minus y sub 1, y sub 2, plus I times x sub 1, y sub 2, plus x sub 2, y sub 1. So here's the real part, and here's the imaginary part of the product of those two complex numbers. Now, there's an important operation that you can use for complex numbers, and it's the complex conjugate. And as you'll see in problem 8, it has a very simple command in Python. Okay, so what do we mean by a complex conjugate? Well, suppose I give you a complex number, z equals x plus iy, and let me suppose that I want to calculate the complex conjugate of it. Well, what that simply means is you take your original complex number. Let's clean up things a bit here. And you replace I by minus I. That's all you do. There are some authors who use z with a horizontal bar on top of it to define a complex conjugate. All right. So turns out that complex numbers have a magnitude. They have a absolute value. And they have something called the modulus. And all three of these creatures mean the same. So the magnitude modulus or absolute value of a complex number is going to be defined. So 3 vertical bars is defined as, it's going to be the creature you get when you take the complex conjugate of that complex number, multiply it by the original complex number, and then take the square root of the result. So let's see what this is. Well, I know, let's start with z first. I know what z is, right? It's x plus I, y. I know what the complex conjugate of z is. It's just what you get if you replace I by minus I. And I want to take the square root of that object. I already know how to multiply complex numbers. So I get x squared minus iyx plus ixy. And my last term becomes y squared times I times minus I. That's so important. Let's write that down. So it's I times minus I, y squared. I squared is -1. So -1 times a minus sign is going to give you +1. This term is going to annihilate this term. So my final answer is x squared plus y squared to the 1/2 power is going to be the norm of a complex vector. And note that this thing is a real number. So even though a number can be complex, its magnitude, absolute value, or norm is still going to be real, measurable. So here's something that we have stumbled on to that is useful. If you took this original expression that we got, here, that we obtained here, and rewrite it, and let's just say we square both sides of this equation, we've discovered something interesting. 1 over z is going to be the complex conjugate of z divided by the norm of z squared. So we know what it means to take creatures that look like 1 over a complex number. Or we know what it means to take 1 and divide it by a complex number. We know exactly what it means. We just have to evaluate that numerator and that denominator. Okay. So how do we visualize complex numbers? And there's a very, very neat way of doing that. We can recognize that we start out with real numbers that lie along the number line. And the extension of that number line into the plane will define by an imaginary axis. So this is not the same thing you do when you deal with real numbers. You're plotting real numbers in 2 dimensions. So here the x-axis is the real part of the complex number. Here the y-axis is the imaginary part of the complex number. So this dot here is a complex number. That's what it looks like. And this creature that I've written down is called the complex plane. And it's the set of all points in a 2-dimensional complex plane. Now, trigonometry is going to come to my rescue if I want to get a better picture of what's going on here. So I'll take my ruler. And ask myself, I've got two creatures. I have an angle theta, and I'll have a vector that has a magnitude, which I'll call r. So trigonometry tells me a lot. It tells me that the norm or absolute value or modulus of this complex vector is r, and that's x squared plus y squared to the 1/2 power. So r is the length of our vector, and it has a name called the modulus. Theta is an angle that the vector makes with the x-axis, which is the real part of z, and she's called the argument. Okay, what else does trigonometry tell you? X equals r cosine theta, and y equals r sine theta. So x equals the modulus r times the cosine of the argument, and y equals r, the modulus times the sine of the argument. And the tangent of the argument is just the ratio of the real numbers y and x. Okay, so we need some tools to get a better understanding of what this vector or point looks like in my two-dimensional complex space. So the tool or tools that I'll use are things that you've seen from elementary calculus. So I ask you to remember or recall, and if you have some issues with this, I'll give you some problems, practice problems on this in a future problem set. You can write down the Taylor series expansion for the exponential function. It is as follows. This is known as a power series. And it's a way that you can evaluate what e to the x is. If you want to know what e to the x is, all you have to do is evaluate first term, second term, third term, and fourth term. Knowing x, add those up. You'll get an approximation to e to the x. And if you want a better approximation, just use more terms. And it turns out that you don't have to use a billion terms to get a decent approximation for e to the x. Here, x is a real number or a real variable. Not a number, it's a variable. So you might ask the question, well, can you use the same trick? Can you define a Taylor series expansion of e to z, where z is a complex variable? And the answer is sure, why not? You just replace x with z. But there's a little bit more going on here. Suppose you look at an example where your complex number is pure imaginary. A pure imaginary complex number simply means that the real part is 0. X is 0. So I could write down a Taylor series expansion for z, where z equals I, y. And the first couple of terms are going to look as follows. I have 1 plus IY plus IY squared over 2 factorial plus IY to the third divided by 3 factorial, and that goes on. And it's easy for you to show, and you should do this, that you can break this up into 2 types of terms. First term is going to go like 1 minus y squared divided by 2 factorial plus y to the fourth divided by 4 factorial. Next term is going to be negative, so it's going to be an alternating sign. So that's what the real part is going to be. The imaginary part is going to have an I pulled out, and you'll have a y times plus a minus a y to the third divided by 3 factorial. Again, the signs alternate, y to the fifth divided by 5 factorial, and that keeps going on. This should be familiar to you from elementary calculus. The first term in the parentheses is simply the cosine of y. It's the Taylor series for the cosine of y. And the second term is the Taylor series for the sine of y. So you are left with the final expression. E to the iy is the same thing as the cosine of y plus I times the sine of y. This formula was discovered by Euler. So he got to name it. It's known as Euler's formula. And it's extremely useful in mathematics. It's an extremely powerful expression. And let's see what it tells us. If you took a complex number z and exponentiated it, by definition, a complex number has a real and imaginary part. Using the properties of exponentials, this is just e to the iy. And now we've discovered using Euler's formula that this e to the iy is just the cosine of y plus the sine of y. So if in fact z equals r times cosine of theta plus, so let's look at this from a different way, sorry. So z is x plus iy. Using the trigonometric relationships we got before by looking at x, a complex number in the complex plane, that's just the modulus times the cosine of theta plus I times r sine of theta. Theta is the argument. You could simplify this as the cosine of theta plus I sine of theta. And Euler's formula, so using Euler's formula, we can write any complex number in a polar form. So really, this argument that I started to go down the street, I don't really need that. Let's get rid of that. Why add to confusing a problem when you don't have to? So we can conclude our discussion of complex numbers by recognizing that there are two ways to express them. One way, I can just say a complex number z is just x plus iy, where the real part of the complex number is x, and the imaginary part of the complex number is y. And the other way to write down a complex number is in terms of its so-called polar form, where r is the modulus of the complex number and theta is the argument. Now, if you think about it, these two guys are not all that different. You can express a complex number in at least two different ways. And so see if you can think about how to write down the modulus in terms of x and y, and how to write the argument of a complex number in terms of x and y. And once you have those relationships, you can see that both of these ways are equivalent. Okay, so that's really all we want to say about complex numbers, at least for our discussion of linear algebra at an elementary level. Okay, so the last topic we're going to talk about this afternoon is the problem of inner products. Okay, so at some level, the inner product is the same thing as the dot product. Why we take the time to give it this name, inner product, really goes beyond the scope of the course. But for all intents and purposes, when we talk about the dot product of two vectors, u and v, that's just the transpose of the following matrices. This is going to be the same as the inner product of those two matrices. And I'm going to introduce some new notation for my inner product. So the inner product of vectors u and v, and for the moment, I know we've been talking about complex numbers, but let's assume that these vectors are real. Once we get through all the machinery of seeing how inner products work, if the vectors are real, we can extend it easily to the case where some of the components or all the components, or at least one of them, is complex. Okay, so this inner product has two parts. The first part is something called a ket, and that's just really a vector in column representation. The second part is this vertical bar, which if I fuse these two things together, I just get one. And the thing on the left is a bra, BRA. And that's just a vector in row representation. And you can see where the names bra and ket come from. If you fuse these things together, you get bracket. At the end, I have pointed brackets. Now, for reasons beyond this course, scope of this course, this notation is going to be extremely useful when you start talking about quantum computing, namely designing computers that work faster than modern supercomputers, so you can solve new and interesting problems in drug design, in material design, weather control, etc., and interesting problems in quantum mechanics. So there's a method to our madness why we're using this notation. So let's go through some examples. Here's a vector u. It has a component in the x direction of 9 and a component in the y direction of 12. And here's another vector v. And she has a component 1 in the x direction and a component -1 in the y direction, positive y direction. I can write these vectors as matrices, or these vectors are matrices, and in column representation, they are respectively this and this. This is a 2x1 matrix, and this is a 2x1 matrix. So the question I want to ask is, what is the inner product of u with v? Well, it turns out it's the same thing as the dot product of u with v, and that's the same thing as the transpose of u with times v. I know what u is, and I know what v is. So the transpose of u is simply going to be that vector. V is not changed at all. So I have a vector here, a matrix. Vectors are matrices. This vector is a 1x2 matrix, and this one is a 2x1 matrix. So they're both compatible. So matrix multiplication, multiplying this column by this row, or taking a linear combination of the columns of these two column vectors. Either way, as we saw earlier in this lecture, it's going to give you the same result, 9 minus 12 or minus 3. So my inner product is a real number. So the moral of the story is the dot product of two vectors is the same as the transpose of the matrix U multiplied by the matrix V. And that another fancy way of writing that is in terms of this bracket notation. Which has important applications in quantum computing and in quantum mechanics. Neither topics we're going to spend any time talking about here, but should you see this in future courses, at least you know where this comes from. Okay, so what are some important properties? Important properties of the inner product. And again, this seems a little formal and theoretical, but it's important. These are the rules of the road. This is the grammar of the language that we're going to use. So you've got to become fluent with this set of rules before you attempt to go out and drive on the highway or the Autobahn. So suppose I have three vectors, u1, u2, u3, and I want to evaluate this inner product. And the question is, this thing looks very complicated. So again, A and B are scalars, and u1, u2, and u3 are vectors, and all these guys are real. Sorry, it's a true statement, but I don't want to. So all these guys belong to R sub n. So these vectors could have 1 component, 2 components, 30 components, 1,000,000 components. So one important property of the inner product is that you can pull out A and multiply it by the inner product of u sub 1 with u sub 3, and add that to taking out the scalar B, and then multiplying that by the inner product of u sub 2 with u sub 3. If this is true for the inner product, which it is, then this inner product is linear. Now, you could actually prove this by plugging in the actual vectors. And we're not going to do that, but you could prove this. And you could prove this not just for vectors in 1 dimension or 2 dimensions, but vectors in n dimension. But we'll just state it for the moment as being true. Second thing about an inner product is that here u is the bra vector and v is the ket vector. Well, it doesn't matter. You could make v the bra vector and u the ket vector, and you'll get the same answer. And again, this is something you can prove just using the properties of the dot product and properties of real numbers. So the inner product is said to be commutative. And again, you could prove this. We will not explicitly in this course, but you could do that. Finally, the third property of an inner product is if you took the inner product of a vector with itself, you'll get an answer that's either 0 or positive. And this implies that the inner product of itself is 0 if and only if the vector is the 0 vector. If this is true, let's clean that up a bit. If in fact you have a non-zero vector, then the inner product of this vector with itself is said to be positive definite. So the norm of a vector is just the dot product of a vector with itself. You take the square root of that. That's the same thing as the transpose of the vector. Vectors are matrices times the vector or matrix U, all to the 1/2 power. But that's the same thing as the square root of the inner product of a vector with itself. This, of course, is the norm, length, or magnitude of U. Okay, so that's going to wrap up where we are today. Again, problem set 7. Problem set 8 today's lecture. Will be posted tomorrow. It's a normal site. And problem set 7, the solutions key is available, or probably will be available later on tonight if it's not there already. So what's next? So I just want to take a minute to give you some highlights of what's going on next. We're going to finish our discussion or complete our discussion of the inner product of vectors. Up to now, we've assumed the vectors are real. We will look at the case where they're complex. And it turns out we've got the machinery to handle that. So that's going to be pretty straightforward to deal with. The meat of lecture 9 and the following lectures is going to be realized in the following sentence. Until now, we have viewed matrices as things that contain information. In this case, the information is written in terms of numbers. Those numbers could be real, as you'll see next lecture. They could be complex. Excuse me. If all matrices did was store numbers or store information, then linear algebra would not be all that powerful. We shall see that matrices can act on vectors. So they're not just passive vehicles to contain information. They are active creatures that can act on vectors. And they can change these vectors in some ways. And we are going to spend the remaining 5 lectures of the course exploring how vectors can act as operators. So or matrices. Matrices can act as operators. Vectors can also act as operators because vectors are matrices, but we're going to look at a more powerful situation where a matrix itself, an n by n matrix or a m by n matrix, actually does something to a vector, changes it somehow. So for example, this matrix does something to this vector. And the question is, what does it do? How does it transform this vector? And we'll talk about that next time in lecture 9. Thanks very much.